just about to say that?
No.
Okay. So then, here we go. So we just did, we're doing the derivative of that function. So we have 1 over u now times the derivative of u. So here we go. Derivative of the first one is 1 times the x squared minus 1 to the 1/2 plus. And then we have x times the derivative of x squared minus 1 to the 1/2. So that's, we're going to perform the chain rule. I have something squared, or something to the 1/2. So it's going to be 1/2 times x squared minus 1 to the 1/2 minus 1, which is negative 1/2, multiplied by the derivative of the x squared minus 1, which is 2x. And that would be your first line of the derivative. To me, that's the most important part, that you can get that. Because that means you know everything that has to go in its place. Okay? Now, this can be cleaned up. So let's try to clean it up a little bit. This whole thing in the brackets is actually in the numerator. So I'm going to put this whole thing over x times x squared minus 1 to the 1/2. That's the bottom. And so up on the top here, it's x squared minus 1 to the 1/2 plus 1/2 x. Oops, the 2's cancel. The 1/2 and the 2. So this is x squared times x squared minus 1 to the negative 1/2. That 2 and that 1/2. Okay. Where does the... Got it? Okay. Now, to finish it off, we would say I'd probably multiply both sides by x squared. Here's what I'm going to do. I want to get rid of this negative exponent right here. So if I multiply this top by x squared minus 1 to the positive 1/2, it ends up being negative 1/2 plus positive 1/2, which is 0. See? So then it becomes x squared minus 1 to the 0. So it gets rid of that 1/2 completely. So watch what I'm going to do here. I'm going to multiply here both the top and the bottom by x squared minus 1 to the positive 1/2. Okay? Now watch what happens when we do this. So now I'm going up here. Okay? So this has to be distributed here and here. So x squared minus 1 to the 1/2 multiplied by x squared minus 1 to the 1/2 is just x squared minus 1 to the 1. So it's just x squared minus 1. Then x squared times x squared minus 1 to the negative 1/2 times x squared minus 1 to the positive 1/2 is just x squared. Okay, because that thing that's in the parentheses becomes quantity to the 0 power. Okay. Then in the bottom, we distribute, or it's not really distributing, we're just multiplying, x times x squared minus 1 to the 1/2 times x squared minus 1 to the 1/2 gives you x times x squared minus 1 to the first power. So it becomes x times x squared minus 1 to the 1 power, because it's 1/2 plus 1 is 1. And so looking at this whole thing, this should be 2x squared minus 1 over, you can leave it in factored form or not. Kind of depends what you feel like. But that's where we would end up with. Okay? Now that would have been the approach that you would have taken based upon what I taught you. Okay? But it's possible for you to look at this problem and say, hey, wait a second. This is the natural log of a product. I know there's a rule that if the natural log of a product is equal to the sum of the natural logs of each one of those individually. So in other words, instead of rewriting this like this, I'm going to rewrite this like this. Y is equal to the natural log of x plus the natural log of x squared minus 1 to the 1/2. See what I did there? I used the fact that there's this rule here, the natural log of a times b is the natural log of a plus the natural log of b. That's the rule that I used. So it's the natural log of x plus the natural log of x squared minus 1. But wait a second. There's a 1/2 right there. With log rules, I can bring the 1/2 down in the front. So I'm going to rewrite it again. Notice before I'm even finding the derivative, y is equal to the natural log of x plus 1/2 times the natural log of x squared minus 1. I haven't even found the derivative yet. I'm just cleaning up the problem before I do anything. Now I'm going to take the derivative. So when I take the derivative of this becomes y prime is equal to, what's the derivative of the natural log of x? 1 over x. What's the derivative of 1/2 natural log of x squared minus 1? Well, the 1/2 is a constant multiplied by 1 over x squared minus 1 multiplied by 2x. Okay? Now the only trick is to wonder if that thing in the blue is the same as what's circled in the black. So let's see if it is. So let's just clean this up. I got 1 over x plus 2's cancel plus x over x squared minus 1. Okay. So I got two fractions. They have different denominators. So I have to multiply each fraction by the denominator. So this x gets multiplied by, if this becomes, I'll write it like this, 1 over x minus 1 over 1. And the other one is x over x squared minus 1 multiplied by x over x. Look closely at that. All I did was multiply each term by what it was missing. The first one was missing the x squared minus 1. The second one was missing the x. Well, now both of them have the same denominator of x times x squared minus 1. It's just a matter of adding the numerators, which is x squared minus 1 plus x squared, which, if we simplify it, matches. So what's the best way? The second one seemed like it went faster, didn't it? So if I was doing the problem and this was a problem on the AP test, I'd probably approach it that way. But notice with both of them, you had, after you did the calculus, you had to do some algebra to get to the end result. That make sense? So we end up with this way that we have to kind of analyze each. Have enough experience so that you know how one situation might work out better if you do it one way versus a different way. And that just comes from experience, which means you just got to do a lot of problems. Okay. All right, well, we have two questions on the back. that are both asking the same thing, but they are different situations. So the goal here is to find the equation of the tangent line for this crazy thing here at 1, 0. Well, the directions are always the same, right? I should say the solution steps are the same. If that's it, I got to find the derivative. I got to plug in the x and the y's, whatever, to find the value of the derivative. That's my slope. And then I'm going to use the point to write the equation of the line. So it's just a matter of being able to do it. So here we go. From the top. 1 plus dy dx plus 0 equals. Then the derivative of the natural log of x squared plus y squared, 1 over x squared plus y squared, multiplied by 2x plus 2y dy dx. It's implicit differentiation combined with the natural log. Okay, each one of those things we got to use whenever. Now, I'm going to do a little trick here that I can't remember if I've done in this class yet, but the goal is we just need to find the value of the derivative, right? And in most problems, we solve for the derivative, dy dx, and then we just plug it in. But I'm going to try to be more efficient. I'm just going to plug in the x and the y's right now. And then the only thing that's going to be left is dy dx that I could just solve for. It's going to be a faster way to get to the value of the derivative. So let's do it. So everywhere you see an x or a y, we're going to plug in the 1 or the 0. So this is 1 plus dy dx equals 1 over 1 squared plus 0 squared times 2 times 1 plus 2 times 0. Look at what happened here. It wipes that one out completely. So I just plug the 1 and the 0 in for every x and y. Now what does this get us? 1 plus dy dx is equal to 1 times 2 plus 0. It's 2. Did I do that right? So, therefore, dy dx is equal to 1. Yeah. Yes. Well, you'd have to plug in the x and the y. This is the x and the, because it's going to have a y in it. Y's in it as well. So you can do it the old way, or just in this case, since all we need is the value, we can plug it right in. Okay, well, now we have a point. We have our slope. So here we go. Y minus 0 is equal to 1 times x minus 1. Y is equal to x minus 1. Let's see if that's right. What I've got is I've got this up on the equation. That wacky equation is up there. So we're going to see if this really does work out. So that's what that thing looks like. X plus y minus 1 is equal to the natural log of x squared plus y squared. And I have the point 1, 0 in there. So what's the equation? Y equals x minus 1. And I would say we have found it.
In this situation, we should just plug in the point in that context.
No, because they're going to give you only a point that is actually an existing point on the equation.
So no matter what that one.
The only thing that they could do that would be weird is if they said, oh, let's use 0 as a point, okay? And you see that 0 could be this point here, okay? Or it could be this point down here, wherever that one belongs. You know what I mean? But what we've got here is just the single point. All right, I do this on purpose so that you see that the visual that goes with that totally and completely abstract thing there. It's so hard to imagine what that looks like. It's like impossible to figure that out. Oh, little side note, look at that tangent line. Now this is a weird tangent line. Why is it weird? It like slices through the function, okay? But this is still a legal tangent line because it has to go from being tangent here to being tangent here. So at some point, it has to cross over. And that's totally okay. All right? It does it on the sine wave all the time. Every time it has to do the flip-flop. And so this is okay. Be okay with this. This is okay. Even though a tangent line, we think, well, it can only touch it at one point, and it's supposed to stay on the same side. It doesn't have to.
What if the point that they give you has a vertical slope?
What'll happen is when you plug in dy dx, of all the values, you'll get an undefined answer. It'll be like 1 over 0, which means that, okay, at the x value, that's where you're going to have the vertical tangent, which happens on a circle, the top half of a circle. If you have a circle and you're going to go tangent right here, you can draw the tangent, but you can't identify that tangent with a number. So we say the function is not differentiable at that point. And if you did a dy dx, it would be undefined. Good question. All right, well, let's do this other one, this crazy one. Y squared plus natural log of xy equals 2. And then we got to stick it in for e comma 1. So here we go. 2y dy dx plus derivative of the natural log of xy is 1 over xy times the derivative of xy. Now you should be getting pretty good at derivative of xy. Okay, so it's 1 times y plus x times dy dx. It's equal to 0. I'm going to do the same thing I did in the last one. I'm going to plug in e and 1 for the x and the y, and then see what happens. So here we go. Let's do 2 times 1 times dy dx plus 1 over e times 1 times 1 plus e dy dx is equal to 0. So what does this give us? 2 dy dx plus 1 over e times 1 plus e dy dx. So it wasn't as fun as that one because there wasn't any zeros in it. So let's let's distribute. I would solve this one by distributing the 1 over e. And let's see what we get here. We get 2 dy dx plus 1 over e plus dy dx is equal to 0. And if I got 2 dy dx's added to 1 dy dx, that gives me a 3 dy dx equals negative 1 over e. And then divide both sides by 3. I get negative 1 over 3e. That's my slope. Which is about how much, roughly? Negative 1/8, negative 1/9, right in that ballpark. Okay? So it's about negative 0.1-ish. Okay? Just to get a sense about you. All right. Y minus 1 equals negative 1 over 3e times x minus e. That's the equation of my line. And then some form, you can simplify it from there. I don't know what the back of the book gave you. That's number 80. So you have to go on Slater to see what they got. Good? Okay. These problems just take practice. It's almost like if you want to go to state in swimming. You don't just go there by watching somebody else do it. You have to put the time in. You got to put the laps in, the yardage, all those long nights where you just wanted to go to sleep. You were just hungry and tired and you couldn't take it anymore. But you do it anyway. And then you get to go to state. Or it's like performing in a musical. It doesn't just happen all by itself.
I wish it did. Talk to Mr. Carter about that.
Mr. Who?
Mr. Carter.
Why?
There's a thing called observational learning.
Oh.
Mr. Carter very, very firmly believes in it. We fought back and forth very many times about that.
Okay, open up your notebook and put in inverse trigonometric functions. Okay, so your calculator has the ability to do the 6 major trig functions, but then it also has the ability to do the inverse. Okay, you may recall that in something, I think you probably did it most likely in geometry, where if you wanted to find the angle, then you inversed your answer. Remember that? When I was teaching geometry, I said it's just like Beyonce. And I even did the dance. The single lady dance.
Like that? Or that? Okay.
Because if you because I think the original words of the song were, if you want to find the angle, then you inverse it.
Oh.
I think that's what it says.
I don't understand. Can you show
Oh, we're running out of time. Okay, so what we're going to talk about is inverse functions. And it's 6 brand new functions, but they are all related to the functions that we've already drawn. Okay? So for example, here is the sine wave. Okay? Now, the inverse of the sine wave, now we just studied inverses, right? They are reflections over the line y equals x. So I'm going to attempt to draw this. If this is the sine wave, then the inverse sine would have to do something like this. Now, do you see it? It's a reflection. You got to tilt your head to the side. And then it would go on. Can you see it? So the graph of the purple is the inverse of the graph of the red. It's the sine wave and the inverse of the sine wave. Okay? The only problem is the inverse is not a function. It fails the vertical line test miserably. And the secret here, as we say here, is that it's a function. So what we do is we eliminate any part that's going to cause it to be not a function. It's extremely boring. Because notice the function only goes from here to here. That's it. Because if it extended any further, it wouldn't be a function anymore. Okay? So it just goes from here to here. Now what's kind of fun about it is, what was the range of the sine function?
Oh, range. I'm sorry.
Negative 1 to 1. And so the domain of the inverse sine is the opposite. It's negative 1 to 1. See? Does that make sense? So this one went from negative 1 to 1 this way. This one goes from negative 1 to 1 this way. Does that make sense? And then they just simply restrict it from, I think they go from negative pi over 2 to pi over 2, because that's the part that would flip. So negative pi over 2 to pi over 2 is the x. Okay? Now, so that's the sine, that's the sine and the arc sine, they call it. Yeah, is the domain. Negative pi over 2 to pi over 2 is the domain for the arc sine. Yes. Well, no, it's domain because it's still what you're plugging in. It's what you can find the inverse of.
Okay, so on the sine wave, that's what the domain is.
Yeah. If we go back here, see,
Gotcha.
look over there. See where the x is?
So
On the arc
we're referring
sine.
to the domain still in the sine.
Yes. It's still it's still the x value that you're finding the value of. Okay, so here's the cosine. Okay, so if we did the switcheroo across y over x, the only part that we accept is that little smidget right there. Yeah. So that's that one. And then the tangent, here's your tangent function. Okay. Ready? Arctangent. It only gets one of them, because if it did all of them,
That'd be unfortunate.
fail the vertical line test again.
This is just disappointing.
Yeah. That's why we don't talk about them very much.
Like, oh.
Now, on there's all this stuff out here,
Never trust machine.
and you can then find the derivative of each.
No?
Not ice. Okay, so here we go. I'm just going to give you the U, because that means that makes the most sense. Okay, 1 minus square root. Nope, du dx, the derivative of u with respect to x. No, there is squared. 1 minus u squared. Okay, so picture every single function that we had, that we just drew, is a new function, which means that it has its own derivative that is associated with. Well, it turns out that the derivative of the arc sine of something is equal to 1 over the square root of 1 minus u squared times the derivative of u with respect to x. Now, there's a whole proof of it in the book. Not very fun, though, so that's why I don't really do it. So let's use this one as an example. If I say to you, what is the derivative of the arc sine of 3x? What is the derivative of the arc sine of 3x? Okay, who's u? 3x is u. Okay, so it's 1 over the square root of 1 minus 3x squared multiplied by the derivative of 3x, which is 3. So your final answer is 3 over the square root of 1 minus 9x squared. That's the derivative, which tells you the slope of the line tangent to the function, which is the arc sine of 3x, which, if I put this in here, the arc sine of 3x, this is just so boring. This poor guy right here, that's all he is. Okay, so notice its relationship to this one. Okay, higher amplitude. Okay, higher amplitude means that it gets stretched further this way, okay, vertically. So the slope of the tangent line to this blue graph at any given moment is 3 over the square root of 1 minus 9x squared. Okay. Now, the table in your book, the one I told you, page, yeah, 374, I think, has the list of all of those derivatives. Go ahead, memorize them, try to find patterns, whatever. It's one of the very few times I'm just going to say, I'm not going to do anything more with this than that. You will see one question out of the 28 free, multiple choice questions that is on this. Yeah, they have 6 for each one.
And they also become work.
Yes. We're going to practice that a lot.
Good.